All right, folks. 4-2. We are analyzing functions again. This is part 2. There is a third part, but we won't get to that until after Christmas break. So it'll be a good review when we come back. This is looking at relative extrema and graphing polynomial functions. Okay, we've already talked about this. Relative extrema is talking about maxes and mins. Okay, so, and we did this when we were doing like increasing, decreasing functions. So like when you'd have your table, blah, 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 all that good stuff. Let's say we have this going on here, and he is increasing here. So let's say we have a table and we have increasing here. He's decreasing here, and then he's increasing here, right? Okay, I usually put like little arrows down below it, and then I can see for sure. At this point, what's he doing?
Absolutely nothing.
He's a maximum, right? Because he's increasing, then decreasing. Here he is decreasing and then increasing, so he is a min. Do you see how that works? Okay, you guys already know this. All right, so down here, they have example 1. There's not really much for us to do on example 1. They're just matching up this stuff. It says that x squared, so this, just so you know, this bullet point goes with this graph, right? The second bullet point goes with the second graph, etc. Do you see how that works? X squared has a relative minimum at x equals 0, which is right here. This is a min, but he has no relative maximum. He is decreasing and then he's increasing. He has a minimum at that point. Do you see how that works? X cubed, which is the second bullet point, looks like this. He has no relative extrema. So like this point right here is not a max or a min. He is called a, do you remember?
A vertex.
Nope.
No, what is it?
What is he? He is a poi, which is a point of inflection. He is changing concavity at that point, okay? Bullet point number 3. It looks like this graph. He has a relative maximum at -1, which is this guy right here, and a relative minimum there, right? Okay? The 4th bullet point is here, and he has 2 minimums and a maximum point. Okay, by the way, just so we know for sure, those 3 points, 2 of them are mins, 1's a max. What is his derivative at that point?
0.
Derivative is slope of the tangent line. His slope is going to be 0. So when I set the derivative equal to 0, that's going to find those maxes and mins for me, right? Make sense? Okay. This third guy, or the last guy, he is the graph of sine, or cosine. Cosine. He's the graph of cosine. And he has relatives and maximums and minimums all over the place. Like every interval of like pi and 3 pi and 5 pi and 7 pi, he has a minimum. Every interval of 0 and 2 pi and 4 pi and 6 pi, he has a maximum. Right? So the maxes occur, you don't have to write this down. Maxes occur at 0 plus 2 pi k is how we write that. Because every interval of 2 pi after 0, he is going to have a maximum. 0 and 2 pi and 4 pi and 6 pi and 8 pi.
0
Yeah.
What?
Why do you have in plus 0? 0
You
plus.
could just put 2 pi k on there.
Just because it's going past 0.
Yeah, right. Right.
Can you zoom
This
out?
one would be pi plus 2 pi
I
k.
see, like if it's negative, then it just 0 minus.
Right, because k could be like a -1, in which case it would be negative 2 pi. Yep. So this is every interval of pi, like pi and 3 pi and 5 pi and 7 pi, etc. You don't have to write that down. But it's just saying like where the maxes and mins are at, you could have different scenarios of different things happen. These guys are all polynomials, but this one is not a polynomial. This is a trig function.
No. The 2 middle guys. The
What?
green and the black graph.
What?
Like the first one's a minimum, the second one's a poi. What's the third and the fourth?
He has a max and a min. Max and min.
Oh, both.
This guy has a max and 2 mins.
Okay.
So for the one on the
Okay.
right, it would have a poi every pi though. It wouldn't be 2 pi.
For the this function, he has a poi right here and right here and right
So it'd be
here.
every pi.
So that would be pi over 2, I think.
Oh.
And every pi after that. Because the
Why?
distance
Okay, that's
between
what
those
I
two is
mean.
pi.
Oh,
So
okay.
pi over 2 is his first place plus pi k instead of 2 pi k. Does that make sense? That's where the poise would be. Yep, good question.
And they're poised because they're changing concavity.
Because that's where he changes concavity. So like here he's concave down, here he's concave up. So the halfway between mark is where he's a
Even
poi.
if it's not like.
What?
Even if it's not like doing stuff, weird stuff, like going like this? Or what are those called?
Oh, cuspid?
I don't know.
A cusp?
Those
Like
aren't
this?
points, though, are they?
No, because he's concave up here and he's concave up here.
What are those called?
A cusp
No.
or a cuspid.
That's a fake word.
It's not a fake word.
Okay, wait, can
Why
you
would they feel like
zoom in on that?
Oh, right here. There we go.
That graph. Oh.
Yeah.
There.
Point of non-differentiability.
There we go.
There you go. Because you can't find the derivative.
Pawn.
You can't find the derivative of this guy.
Pawn.
what?
Pawn. He's a pawn.
He's a
Sure. Point of non-differentiability. So you can't find the derivative there. You can't find the derivative there. But at maxes and mins, you have a derivative, and his derivative is 0, or his slope is 0,
So why
right?
are those ones not?
So to
Now, the
find-
reason why they don't have like horizontal tangent lines like those ones do is because like a tangent line touches at only one place, right? But think of this being like a tippity tip right here, right? I could draw technically a line that way and he would only touch at one place, true? Or I could draw a line this way and he would only touch at one place, right?
Yeah.
So like I could draw multiple lines through that exact dot and it would only touch at one place. Versus this guy, I couldn't slant him to the side because then he would graze there and wouldn't graze at the top. Like the only tangent line I can draw through that line is one that goes horizontal.
Okay, so to find a
Or
max and
vertical.
mins. Oh, sorry.
Okay, what? Go ahead. A vertical tangent line? I mean, he wouldn't have a vertical tangent line. Like that's not a thing. You can't do that. You can't draw vertical tangent
What
lines.
is that?
Well, there is vertical tangent lines. That is such a thing. But for maxes and mins, they don't have vertical tangent lines.
What would the derivative of a straight up line be? Infinity?
What straight up and down line is not a function to begin with.
Darn.
So we can't find the
Vertical
derivative.
line test.
Vertical line test.
Vertical line.
Yeah.
Wait, so to find max and mins, we need to set the derivative equal to 0.
Yes.
Is that what you said?
And then plug in and find where he's increasing, decreasing, and that will tell you max and min. Okay, these are called critical points. By the way, circle the word critical point. We've already established that those are critical points. Moving on to, critical points.
Yeah.
Let's move on to example 2. Find all critical points of this function. Okay,
Where?
so
Oh,
we set the derivative. We take the derivative of this guy, which is 3x squared minus 3.
I don't
No, it's.
No, yeah, 3x squared minus 3.
Yeah.
Okay, and then we set him equal to 0. And what do we do?
Okay.
What should we do first?
Oh, we gotta find the derivative.
We found the derivative.
3x squared minus 3
3x squared
So
equals
add
3. Let's bump the
3.
3 over.
plus 3
X squared equals 1.
divided by 3.
And take the
divided
square
by
root.
3. X squared equals 1.
And the square root of 1 is
minus
plus minus 1. So I have two critical numbers which are at plus minus 1. Does the graph have two critical places?
Yeah.
Yes, two possible maxes and mins, right? And then what we would do is we would create our test intervals, okay? And our test interval would go, we'd have 3 of them. He would go from negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity. Those would be my test intervals, okay? Then I pick a test point. Let's say like negative 2, 0, and 2. And if I plug negative 2 in,
Negative 2, 0, and
I'm just going to cheat. Looking at the graph, what's negative 2 doing?
down.
He is,
Negative.
no.
Increasing.
He's increasing. He is increasing,
Oh.
which means he's plus.
Shoot.
Plus, which means
Okay.
increasing. Okay, what about from negative 2 or negative 1 to positive 1?
What?
From negative 1 to positive 1, what's he doing?
Decreasing.
He's decreasing,
Oopsie.
which means he would have been a minus, okay? Then from 1 to infinity, he is
Increasing.
increasing, okay? He is increasing,
Minus.
decreasing, increasing, which means he has a maximum here and a minimum here. Yeah?
Wait, so we're doing the exact same thing, but we're just finding max and mins
Yeah.
rather than just finding if it's increasing or decreasing.
Correct. Correct.
So we're just going like a
So
step
we're doing
further.
the
We're just going like a
same thing.
half a step further.
Got it.
Yeah.
So
Yeah.
what we ever need
Um, Now, real quick, one other thing. What is the maximum number of critical points that a polynomial can have? What's the rule?
n minus 1.
N minus 1. If n is the degree, if this is a third degree polynomial, what's the maximum number of high and low points you can have? 2, right? N minus 1. Got it? So where n is the
Okay, why?
the thing. Why?
Because it's
Because on both sides it's gonna have like if it's 1, 2, 3, 4, 5.
Equals
On the two
what?
sides of it. It has two sides to every point.
Right.
So if
I don't know.
I don't
so
know
you can
how
only
to
have
put it in
points
words.
in between two sides.
So like an x to the third power function is gonna have 3 chunks on my graph, right? So x to the third power will have 3 chunks, which means I can have at most 2 places where the chunks change.
Yeah.
Is that confusing?
Yeah,
Okay.
but put that into words so that we can write it down.
See, it's hard.
Why?
Because we can start with
Because he can have at most
Geometry said so.
2 changes in direction. He can only have 2 places where he changes direction. I don't know. Because I said so, that's why.
Critical because
Cause it just,
the critical numbers need to
Because
have two sides.
n intervals
it just.
equals n minus 1.
You bringing that back?
If I have n number of intervals, then I have n minus 1 number of changes in those intervals. I don't know. Does that suffice?
Suffice? That's a weird
Yep.
word. How do you spell that?
Suffice?
S-U-
S-U-F-F-I-C-E? Suffice?
Yeah.
We're doing all of
Like,
the...
is that sufficient? Does that suffice?
Okay. N intervals.
If you have n intervals, then you have n minus 1 changes between your intervals, right?
Number
I don't know. I don't know.
in those intervals. I get what you're saying, I think.
Yeah.
Okay. Next one.
I am interested to see how this one's gonna work.
Oh, yucky. Oh, it's gross.
How many critical numbers do you think we should get over here?
2,
2?
3, 4,
1
5.
here and 1 here?
That's
3.
funny.
3? Where's the third one? You're lying to me.
I don't know.
You like to say
I
that,
think,
baby.
but I'm worried about, like, I don't know if that's gonna give us
I was
one.
gonna say,
Okay, let's
get
see.
you not
We'll
to
see.
do
Oh, yeah.
Oh,
Hold
I
on.
know though. I know what's gonna
Hold on.
happen. I know exactly what's gonna happen. Okay, first thing we have to do is take the derivative.
We're gonna have a weird guy.
F of x, f prime of x equals 0. Got it. Let's take the derivative. 5/3 gets multiplied down in front. What is 5 over 3 times 3?
5.
It's like 3 over 1, so it's just 5, right? 15 over 3, which is 5.
5x
5x to the
2/3.
2/3, right? Because I'm subtracting 3/3. Trace, you need to be with us. Minus 2/3 times 15.
10, right? 10.
15 times
Yeah.
2/3
10.
is 10, yes? Okay. Minus 10x to the
Negative half.
negative 1/3.
Negative third, yes.
Okay. All right. So let's figure out what this means. This means 5x to the 2/3 minus 10 over x to the 1/3, or the cubic root of x, right? And then I'm doing that derivative and I'm setting him equal to 0. Right? Maybe?
Oh, is it? It's a. No. What is that called? Is it a block?
Okay,
What is
now,
that?
before we solve this thing, we have an issue here because now we have an x in the bottom. And what can x not be in the bottom?
0.
X can't be 0. That is why I have a cusp, or a cuspid
Yeah, but it's
piece
still touching.
here
How's
at
that
0.
Maybe it's not.
That's okay, because he's touching there because the original equation didn't have a va, right?
work?
But my derivative has an undifferentiable place. That's why he's called a pond, right? Point of undifferentiability. My x in the bottom did not arise until I got to the first derivative, right? So he's not actually a va. He will touch there, but here's where I'm going to have a problem, and that's because my first derivative has a bottom. Okay. All right, now let's solve this guy. What? What are you saying? How do I solve this thing? What should we do first?
Set it equal to. Wait, are we setting it?
I'm going to add this guy over. Can I add the 10 over to the other side? So he'll become positive 10 over the cubic root of x
Sure.
equals 5x to the 2/3 power. This is going to be nice, folks. This is going to be real nice. Okay, now what?
Multiply by the cubic root of x.
Okay, I'm going to multiply by the cubic root of x, but I'm going to call him x to the 1/3 power. right? Times x to the 1/3 power. This is gonna be real nice.
And it makes it
So
x.
10 is by himself. X to the 2/3 times x to the 1/3. You add the exponents. 2/3 plus 1/3 is just x to the first power. And then we
Ooh.
divide by 5. So x is
2.
2. Do we have a critical place at 2?
Yeah.
You betcha. There he is. So this guy was a cusp or a cuspid place because his derivative was bad. Okay? He wasn't bad to begin with. He's not a va. But then we have another place, whatever.
That makes so much sense.
Yeah.
I got it.
There you go. Got it? Okay, and those are our critical numbers. Then we could do our test interval things and figure out where he's increasing, decreasing, that type of thing. Okay? All right, so it says a function has a relative extremum, which is a max or a min. So a max or min occurs at the critical points where the sign changes. So where he changes from plus to minus, or increasing to decreasing, or where he changes from decreasing to increasing. He will have a max or a min where he changes sign, right? So here is a plus, here is a minus, because he's increasing and then he goes to decreasing. So he's going to have a critical point. This is still called a critical point, even though he's a cusp, because he's increasing then decreasing. He's switching sign, or switching increasing, decreasing. So he's still a critical number. He's just not a max or a min.
Wait, it says
Okay.
stationary point. What does that mean? It's not a stationary point.
They call like maxes and mins stationary points, and they call cusps non-stationary points. I don't ever use that terminology, but that's what they call. Yep. So cusps are not stationary points. Maxes and mins are stationary points. Whatever. Okay. Same thing with like this looks like an absolute value function, but he is decreasing and then he's increasing. So that is a critical point. Something critical is happening there, but it's not a stationary point, or he's not a max or min. Okay? This guy's a critical point, but he's not a increasing, decreasing. He is a poi. This guy is also a poi. This guy is also a poi. And this guy is also a poi. He is not changing from increasing to decreasing on that bottom row for any of those, right? This one, he's increasing the whole time. This one is decreasing the whole time. This one's increasing the whole time. This one's decreasing the whole time. So those are not going to be maxes and mins. Just points of inflection. Okay?
Wait.
Good?
No.
Can I use the bathroom?
Really?
Yeah.
I don't care. Go. Okay? Good? All right, this is the backwards wackadoo thing. Are you ready?
What?
This is a backwards wackadoo thing.
Are we doing example 4?
We're on example, oh, there was an example 4.
Yeah.
Example 4 was like the same as example 3.
We
Oh,
said in
oh,
example
oh.
3 there's a function.
Example 3,
Critical points.
yeah, he had a critical point at x equals 0 and a critical point at x equals 2. It suggests that he has a maximum at 0 and a minimum at 2. Confirm this using the first derivative test. Okay, so what our critical numbers were 0 and 2. So he's doing something from negative infinity to 0. And he's doing something from 0 to 2. And then he's doing something from 2 to infinity. Those are my critical numbers. Okay? All right. We have to pick a test point, so let's go -1, 1, and 3. And we're plugging that into our first derivative. Blah, but our first derivative is so disgusting. Okay, first derivative was 5x to the 2/3 minus 10 over the cubic root of x. Blah. Okay. I'm plugging in -1. And when I plug in -1, we get a positive number.
How?
Because we do. Because I cheated and I looked at the graph. That means he's increasing here. I don't want to plug it in. When I plug in +1, I get a minus. That means he's decreasing there. When I plug in 3, I get a plus, which means he's increasing there. I totally cheated. You can plug them in if you want to. That would just take us extra time, and I don't want to do that. Okay? So he's increasing, then he's decreasing, then he's increasing again. Okay? Now, This guy looks as though he is a maximum. Except, how did we know 0 was a critical number? Because x cannot equal 0, which means he's not actually a maximum. He is a pawn. He is a pawn, a point of non-differentiability. Okay, because that's how we knew 0 was a critical number. Now, 2 we got as a legit critical number, right? He is like a perfect critical number. Okay, and because he's decreasing and then increasing, this is in fact a minimum. Okay, so we have a minimum at 2 comma something, right? Do we know what that something is? How do we figure out what the something is? There's a min at 2 something. How do I figure out what that something is? Plug it into the original guy. If I do, I'm going to cheat and we have no idea because the graph doesn't tell me. So we're just going to put question mark because I don't want to plug him in because he's disgusting and I can't do it in my head. And he's going to be a decimal number, right? So he has a min, but then 0 is a point of non-differentiability. So he is not a max. Even though he looks like a max, he's not actually a max. Does that make sense? Clear as mud? Okay.
Basically, if we find it as in, like, we can't have it, it's going to be a
Yeah, if we find it and it can't work out that way, then
Are we saving the
Will
last
that only
page for
work
tomorrow?
if we have the, or it, in trig, there's like 2 things where we can't have 0.
oh, a negative inside a square root and division by 0.
Yeah.
Yeah.
So will we ever have the square root thing? And this, or x can't, or I don't know. Maybe not.
Yes, if this was a square root, we would have had that occur just now,
And
right?
it could have been less than 0.
Yeah. Yeah.
So like there would be a graph on that side.
Like the graph wouldn't even exist over there, so we wouldn't even probably care, I guess, at that
So can
point
we,
because it wouldn't.
are we saving
exist
the
over
next
Let's do
page?
one more. One more thing, and this is a wackadoo weird thing, and you're gonna really hate me. It's really easy, okay? So the steps that we have right now, I'm gonna say to find max versus min.
We
Min.
chart it.
Okay? Here are the steps. Derivative equal to 0 to get critical numbers. Okay? That's step number 1. Step number 2.
Chart.
Test points to find max min, or to find increasing decreasing. Basically chart. To find increasing decreasing. And then I'm going to say locate max min. Okay, from there. So derivative equal to 0 to get your critical numbers. Then we test the points to see where he's increasing, decreasing. Locate max min. That's the steps that we have to go through, the hoops that we have to go through to find the
How do
maximum
we-
and minimum
How
at this
do we
point.
know
0?
The
What?
max and the min are.
On that guy.
What you talking about?
What's 0 on that graph right there?
What's
He's not a pawn, but he's not a.
He's a poi. Because he's concave up here and he's concave down here.
So that's not going to be a critical number.
No, it'll be a critical
Oh, for
number.
second derivative.
But
Right?
we're not taking
Yeah.
second derivative because
Critical number for second
A,
derivative.
P,
right?
a POI has to do
But we
with
don't
second
care because we're not
derivatives.
doing second derivative. No.
Mm-hmm. Not yet.
Or are we
Just wait.
doing it
No,
now?
we're not doing concavity yet. No. I think this section's only talk about more about maxes and mins. Okay. Here's the funky weird thing. Are you ready? Okay. If we want to go a different route, this is something called the second derivative test. Okay. This is another way of finding where your maxes and mins are, which is kind of a weird, funky way. Okay, but it's easier. Okay. Step number 1. Find. I'm gonna say deriv equal to 0 to find critical numbers.
So is this just another way, or is
This
there
is
like,
another way.
like a specific time I'm going to use this for? Or is this just like another?
There are
option?
certain periods of time where this is faster than doing it this way.
So For the locate max and the min, do we have to plug stuff in to find like what number the max is at and what number the min is at?
For the chart way, yeah. We have to like do the whole chart thing to find your maxes and mins. And doing the chart thing is kind of cumbersome
And
sometimes.
she's asking like the point. We
Yeah.
need to know the point.
Like I can
2, comma,
like
blah, blah, blah.
like doing the chart. I can say, oh yeah, this is gonna have a max, and oh yeah, this is gonna have a min. Do we have to say at what number the max and min are at, or no?
Yeah, they'll tell you usually. Like at what coordinates.
Okay.
Like here it says find the relative extrema. So we would say there's a max at 2,6 and there's a min at 1,5, whatever, right? Okay. All right. So here's the deal. We take the derivative. We set it equal to 0. Let's do that. First derivative.
15x to the fourth
15x to the fourth minus
15x to the second.
15x to the second. I set him equal to 0. Okay. What shall we do?
0. We're gonna take an x squared out.
Pull out 15x.
15x squared. Okay. Left over is
X squared
uh-huh.
minus 1.
X squared minus 1. Okay. Now I set both pieces equal to 0. So 15x squared equals 0.
So x equals 0.
X equals 0, right?
Yep.
Okay. X squared minus 1 equals 0. So x squared equals 1.
Plus 1.
And x equals
Square it.
plus minus 1.
X equals, oh, yucky.
Got it? Those are my possible critical numbers. Those are possible maxes and mins. Okay? Now, if I want to do the chart, I would have to have like 4 test intervals on my chart. Like plug them all the junk in. This is the faster method. This is called the second derivative test. Okay? So, here's the loop.
Okay.
Plug crit numbers into the second derivative.
What's that gonna do for us?
Okay? If you get a positive number, it is a min. This is the confusing part. If it's a negative number, it's a max. That's the confusing part. This is where it's exactly the opposite. You remember last week, right, Reese, you asked me, like, at least plus goes with increasing and minus goes with decreasing.
Yep.
This is the one spot where it's the opposite of what you think. A positive number actually means it's a min. A negative number actually means it's a max. If it's 0, it's neither a max or a min, and it's usually a POI. Okay? So it's not a max or a min. Okay? So let's take those numbers that we got. We'll plug them into the second derivative and see what we got.
Or it'll always be
Or
a
upon.
Poi
Yep.
or upon.
It's either a poi or a pon.
A poi.
Okay? But usually a pon arises from like the dividing by 0 type thing. Okay? All right, so we have our numbers 0 and 1. Here is my first derivative. Let's find the second derivative.
Okay. 60x cubed
60x cubed,
minus 30x.
30x. Okay, let's plug in. I'm going to do f double prime of 0. I'm going to do f double prime of -1. And I'm going to do f double prime of +1. That's my notation that I'm going to use. You see that? I'm plugging in 0, plugging in -1, plugging in +1. Okay?
Well, we're going to set 0, 0.
If I plug in 0, right, 0 here, 0 here, that's going to give me 0, which means he is
Poi.
a poi. He's neither a max or a min. He's a poi. At 0. Do I have a poi at 0?
Yes.
Yep. Okay. -1. If I plug -1 in, 60 times -1 cubed minus 30 times -1.
So it's going to be negative.
This is -60 plus 30, which is negative. He's negative, and negative means he has a maximum at -1. Is there a max at -1?
Yes.
You betcha. Okay. Min, oh, no. 60 times 1 cubed minus 30 times 1. He is 60 minus 30, which is a positive number, and positive means he's going to be a min. Do I have a min at 1?
Yep.
Yes. So,
We did it right.
that is maybe a shorter route than doing the whole dang table thing, right? And that's called the second derivative test. Okay? Second derivative test. Got it? Good? Is that okay for the day?
Yeah.
Yeah, what?
We have 3 or more. We should just do that.
Yeah. If you're only looking for maxes and mins, that is a really fast route.
I have a question. Does this class get harder second semester?
Does it get harder second semester? Second semester we'll start doing antiderivatives,
What the?
which is like
So we
undoing
start
a
with
derivative.
and then we just
Is the whole thing about derivatives?
Antiderivatives, kind of, yeah.
Why don't we just?
Okay, I'm gonna go to the
Because the derivative is a rate of change, and calculus is the study of rates of change. Like a rate of change is like dx dt or dv dt, and all of those are derivatives. Yeah, right?
Why is it called calculus?
What?
Because you're calculating.
Calculus,
Oh,
there's a, like it's Greek for something, I don't remember why they call it calculus.
No, who is it?
Newton
No, yeah, it was Isaac Newton, wasn't it?
and
Isaac Newton
I don't know.
discovered
I don't know
calculus.
either of them. So.
God.
Was it Godfrey?
I thought it was Einstein
No.
that had to do with calculus, no?
No, it's Newton
No.
and. Forget that guy's name.
God.
Godspeed.
No.
I don't know. Okay, I'm gonna stop the video. Goodbye, people.
Gosh, what is his